Good morning. Thank you. Thanks for all of you coming, and for all of you online for joining us with us. My name is David James. I'm a Geographic Information Specialist with the Agricultural Research Service. I work with Mark at the National Laboratory for Agriculture and the Environment. Mark and I have been working on watershed studies for, well, close to 20 years now. And when the opportunity came along to examine how we might be able to take advantage of modern spatial data and interact with the Environmental Defense Fund and the NRCS and others, we thought it was an excellent opportunity. I'm going to speak to you briefly about the database that we've assembled for the ACPF and how it enables the tools to run. I'm also going to spend a little bit of time talking about a sister project of ours, the Daily Erosion Project, one that initiated in Iowa back in the early 2000s. But with the advent of the ACPF database, we've been able to retool that application and take advantage of the high resolution data. So the ACPF database goals are in essence to provide an extensive and consistent geospatial database that allows for the development of these agricultural cooperation planning tools and to implement those at a small watershed scale, a practical scale. I like to think about it. One of the original goals that Mark and I developed was trying to enable conservation planning at the level where conservation practices are put into practice. That's the field level. And we can't look at individual fields one at a time. That would be a little time consumptive. So assembling those at a watershed scale, a small watershed scale, gives us the opportunity to interact with those data at the field level, but to essentially view the information at the watershed scale. Pertinent to conservation planning are three core data sets that we use for doing our conservation planning: soils, land use, and terrain. And again, the attempt here is to develop a consistent data structure, which will enable us to develop tools that will run across any of the watersheds in the database. Additionally, we've incorporated these into ESRI's Cloud Geodatabase format. What that does is it allows people to bring their data, people that are familiar with ESRI's data products and managing data in the Cloud Geodatabase structure. It allows them to bring their data and their tools and bring them together with the ACPF. So at this point in time, we're looking at a database that extends across 4 states, although we're actively adding additional data. Here you can see the 4 states, Iowa, Illinois, are completely filled out. Southern Minnesota, eastern Kansas. We're looking at approximately 5,000 individual watersheds that are available. Kansas will not be available until right around the 1st of October, when we plan on releasing the updated version of the database and the toolbox. That will incorporate land use information current to 2015 growing season. Somewhere around 80 million acres in agricultural land is addressed in these databases. That's out of a total of 114 million acres. I mentioned the practical scale when we start to examine how we want to manage these data collectively. That's what my job is. And then provide them to users who are interested in addressing local conservation planning attempts. So here's Iowa. You can see the black border down the middle of the state separating the Missouri River drainage from the Mississippi River drainage. Within those, there are 58 Huck 8s, 57 Huck 8s. So the dark blue lines, 390 Huck 10s. Those of you familiar with hydrologic unit codes understand these are nested watersheds that the USGS and the ARCS have developed over the years. And then for the Huck 12, the unit of implementation, if you will, there's 1,700 in Iowa alone. As we look across the landscape again, 5,000 now are available or will be soon. We're adding additional watersheds in Wisconsin, northern Missouri, southeast Nebraska. Our work with Iowa State GIS facility and the Ag and Biosystem Engineering folks going to add the rest of Minnesota and eventually hopefully flush out the rest of the areas that Mark showed earlier that we're working with with the ARCS. So I'm going to go through the evolution of the core data sets that we've developed. But probably fundamental to all of the ACPF is accessing data at the field level. We're able to obtain the pre-2008 CLU field boundaries data set back when it was still a public data set. This formed the basis for our assembling the field data. And it was not an easy task to do. You can see here a single county's worth of data. And the data are not particularly well formed for that one single county. And that's because that FSA office will manage producers' fields regardless of where they are. That county office could find that they're managing fields hundreds of miles away in some cases. So this is a single county. Our goal here was to try and bring this into a single county. So what we did is we would assemble the counties around the instant county, the yellow county in this case, and we would swap back and forth the fields from the surrounding counties to capture all those satellite polygons for a particular county to try and bring them together spatially. In the end, we would find ourselves with a single county's worth of field boundaries, and we would then use that as the opportunity to enhance, update, if you will, these data to be more useful for conservation planning. We're not interested in administrative roles. We're not interested in whose land in particular the fields belong to. We only want to understand how those present opportunities for conservation planning from a landscape perspective. So with the aid of many students over a 2-year period, we took the mass crop data from 2009 and those counties worth of land use data, or excuse me, the counties worth of field boundaries, and looked for those fields where land use was a single crop was not the dominant condition. So any polygon where the dominant crop was less than 75% of the field, we identified that as an opportunity to subdivide that field into a crop-specific field boundary. As you can imagine, it was a very time-consumptive process. We went through a lot of different students, and understandably so. And we were thankful for them because they could see what they were doing and we could not. In the end, we ended up with a data set where we were confident that we had captured most of the field variability in terms of specific crops for 2009. We realized that, yes, it's 2016 and those things are going to change. But, from a data set that we can provide across an extensive area, being able to set the plate for future users to edit those field boundaries and make them more current to their uses. We think that we've come up with a nice set. The land use data that we use comes from the mass crop data layer. The mass crop data layer is asked folks publish every year. Detailed satellite-derived land use information that's crop-specific. The national collection goes back to 2008. I believe Wisconsin goes back to 2006. We will assemble for our database those data going back to 2008 through 2015. We take those data, and for each polygon in a PUC 12, we'll calculate the zonal majority for land use for each year, and the percent that that majority class makes up for that polygon. And as you can see, over the years, the mass crop data layer varies in the resolution, and if you look at the actual attribution, the number of classes varies as well. They've done a very credible job of increasing their capabilities. Now they're using Landsat 8, which is a very nice platform, and they're also using a lot of European satellites and other ones as well. So we're very pleased with the quality of the data, especially in recent years with regard to the land use. And so as you can see across the bottom panel here, this shows the majority crop in 2009 and the percent that makes up of that field. Then you can go all the way across, and for each year, we carry that in our crop history table. While that's very useful information, we wanted to become a little more aware of crop management practices. And so Mark and Sarah and I attempt to develop essentially a crop rotation assignment based on our different years of land use. So up above, you can see for each field identified with this field boundary ID and the size. We assemble a 6-year string that represents the majority class land use for each polygon. We also summarize it in counting the number of different crops, count the number of years of continuous corn, and whether or not it was a mixed use or not. That is, whether or not the dominant crop was less than 75%. We then wrote a rule-based set of programs that examines that crop rotation string and other pieces of information here, and assign what we call a general land use. It's essentially a crop rotation string for each field, and you can see here in this map how these things fall out. Bright yellow being a strict corn soybeans rotation, and then various levels of continuous corn added in, and so forth. We've recently modified this very significantly when we added Kansas, and of course we started seeing a lot of wheat come into play. We had to rearrange our rule-based programs to kind of capture those land use patterns. We think that we've come up with a pretty good set. This is the land use assignment classes. So for essentially the dominant crop in that system, we have a continuous class. So continuous corn could be continuous wheat or continuous soybeans in some cases. A perennial rotation, that would be a rotation that has a dominant crop with some permanent cover, usually some form of alfalfa or hay, that is included with that rotation, and an annual rotation. So that dominant crop with some other row crop in the mix. Then a bunch of other ones, especially that pertain to wheat, especially the wheat fallow and the corn fallow that seem to appear in Kansas quite often, wheat, soybeans, and so forth, and double crop rotations are broken out as well. We then have a pasture class, which is very inclusive. It's very difficult from a remote sensing perspective to actually identify discrete grass-based systems. And so we do a lot of lumping here: pasture grass, hay, meadow hay, alfalfa, kind of gets lumped into that structure. We also, when we find timber class with a grass class, we figure that's probably some kind of pastured woodlot, and we include that in this class as well. A mixed agriculture class that kind of is a cleanup class where we have a whole different set of things going on and we really can't figure out exactly what they're doing. One that I thought that was very interesting to me, we were able to identify those fields that somewhere in that 6-year span of time was actually classified as water. So essentially we decided to assign that a flood-prone cropland class to identify those low-lying areas that might be subject to flooding on occasion. And other classes, more non-agricultural, forest, water, urban, and the like. So that represents the mix of classes that we have within our land use data set. If we look across the 4 states, we're now looking at, again, 80+ million acres of agricultural land, 1.2 million agricultural fields. The yellow classes that are highlighted pertain to something with corn in it. We're looking at over 70% of the landscape, even with Kansas included. Over 70% of the landscape is in some kind of corn production. And notably, in this year, 400,000 acres plus of flood-prone cropland. That's down 150,000 acres from the previous 6-year period. That would have been, what, 2009 to 2014. The second component of our data structure is the soils database. We used to be called the Soil Tilth Lab. Most of the guys most of the people at our laboratory are soil scientists, soil physicists, agronomists, and the like. They're very, very keen on soils. And I've developed a number of different applications that access soils databases over the years, and it's always a little challenging because of the manner in which the soils data are managed by the NRCS. It's not a simple database, and so it takes a little bit of effort to try and assemble the data that you wish. But we take great advantage of the soils data that are available, especially the rasterized soils data, the GSERGO data that's available from the NRCS, and of course the full complement of the soils data mart data structure that's available as well. Here's a simple map of a single soil property. This is a taxonomic class, I believe. But here are the tables that we access when we assemble the data for the soils database in the ACPF. We have to access the full database, assemble it locally, and then write queries that extract these data as we see fit. We then parse that out to each of the individual watersheds along with the GSERGO. So this is the fields, or some of them actually, that we extract. We pull 40 fields from these variety of databases. You can see the numbers there. And because of our moved towards modeling saturated buffer opportunities. We've actually made some custom extractions to understand some horizon-based information that is pertinent to saturated buffer extraction or prediction. So it's an interesting process that we go through. Since the NRCS upgrades or updates, hopefully it's upgrade, their soils database every year, this is a practice that I have to undertake at this point in time. We're trying to work with the NRCS to be able to make it so you can extract these data directly to the ACPF database without having to wait for us to perform that action. Lastly, I'll talk about the high resolution elevation data that we use in the ACPF. We don't provide this information. Managing elevation data is a cumbersome chore. That being said, it is the linchpin to our application. Without high resolution elevation data, we would not be able to model the landscape that we do using the ACPF tools. Mark and I used to work with the data that came from the USGS, the MED, 10-meter data, 30-meter data. You just cannot faithfully represent what's going on at the field level with that resolution of data. So when the state of Iowa acquired statewide LiDAR-derived elevation data back in 2007 to 2010, it provided us with the impetus and the opportunity to start to develop these kinds of tools and to embrace the high-resolution elevation data. But that's not without some problems that are involved, and most of those are an artifact of the fact that LiDAR is a active sensor that only records surface elevation. So every time you see a road, it takes the top of the road. It doesn't account for the fact that there's a culvert that goes under the road for the water to go through. So over the years, we've worked on developing tools and methods for what we call adaptive hydrologic enforcement. I've worked extensively with Brian Gelder at Iowa State University to develop some automated tools. More recently, we've developed tools that we can use in the ACPF to actually do the hydro enforcement of that elevation data. A couple of different terms associated with DEM conditioning. Hydro-flattening allows you, generally provided by the vendor of the elevation data, provide you with flat surfaces for water bodies. So lakes and rivers have a smooth surface. You can see here on the left in those red boxes where we have artifacts of the fact that LiDAR does not penetrate, does not return a signal from a water body, and so we'll end up interpolating from the stream banks across those. We get those typical kind of triangular facets that are associated with that interpolation process. On the right, you see those features are flattened. They present a uniform surface for the water. In the rivers, there is a gradient, so the water won't flow downhill. There are no tools in the ACPF for doing hydro-flattening, so Jim, encourage your folks to get their data hydro-flattened when they get it in Wisconsin, okay? Hydro enforcement is the enforcing of hydrologic flow across the land surface. This requires a significant amount of effort, and it is not something that comes easily. That being said, Sarah's developed a tool that allows you to edit the elevation data, if you will, and create a hydrologically enforced elevation model. When you go upstairs, that's the first thing you guys are going to be doing is figuring out how to make the water flow across the land surface. It's gotten better over the years as elevation data becomes more prevalent at these high resolution scales, that we're going to see more and more data becoming at least partially hydro-enforced, so the level of effort won't be quite as significant. So here you can see just a little indication of what the hydro-enforcement process is. You can see on the upper set of panels the elevation model and a nice symbology there. You can see the channel that's associated with the riparian area that's in the right-hand aerial photography. Without hydro enforcement, you can see in the lower panel the shaded elevation data becomes a single color there at the southern half, and beneath that road. On the right, you can see the flow paths that had to essentially fill that depression and then spill over into the riparian area on the far side. That's not acceptable from a modeling perspective. So this is a case where hydrologic enforcement would have to be conducted. As I said, Brian Giller and I have been working over the years to develop an automated process for hydrologic enforcement. This is primarily Brian's work. That he does a very credible job. It takes a little horsepower to get through it, but essentially what it does is it looks at the elevation model and says, everywhere where you see is kind of a shaded pond behind there, that's the depression where we have impeded flow. He finds, if you can see them, the little red cells that are the deepest cells in that impeded area. He then looks at a radius around that to find opportunities for flow downstream. That would be these yellow cells in this particular slide. He then identifies the best connection by looking at the range and elevation data and the proximity between the two different points, and then actively creates a vector for that line, and that line is then used to cut through those impediments to flow. In the end, you have a fully flowing elevation model. Of course, because it's automated, there's sometimes some issues with where those cuts might have gone, but they can be fixed with some of the tools we have in the ACPF. In the end, we'll have a hydrologically enforced high-resolution elevation model. In Iowa, we now have a 2-meter statewide elevation database for each flow. They are partially hydro-enforced with information that came from the Iowa DNR that in their contributions to the NHD, the National Hydrological Data Set. So that was very fortunate for us, it becomes a very, very useful data set for the ACP. Our intent here was for our study areas, to develop this extensive high-resolution database that will enable the ACPF tools to run at a field level. That's the land use, terrain, and the soils data that we've assembled. And what this does is it provides a consistent structure that allows the tools to run in any of the watersheds that are in the data structure. The North Central Regional Water Network hosts our watershed, our website. This is a map of the data, the current database, and the data that's been downloaded. It was released a year ago, essentially. And so far, we've had 650 plus watersheds downloaded. You can see in some cases significant areas. So down here in Illinois, someone took a good chunk. And then up here in Minnesota, significant amounts of watersheds. I mean, full suck eighths worth of data have been downloaded. And, some of these have been downloaded more than once by different folks. We keep track of this as part of the download process. We have a website, ArcGIS server application that allows you to actually download the data sans elevation data. Like I said before, we're updating the soils and land use data to include the 2015 land use and soils data. They're going to be released hopefully around the 1st of October. It'll include eastern Kansas, and we'll be following on with other states. Look at this slide again. Oh, I guess I don't have that slide. So we are moving on to include Wisconsin. I think we've got 23 counties of eastern or western Wisconsin that have field boundaries that have been assembled and built into the ACPF structure. After we get back the next week or two, we'll probably run through that through the database generation process, which carves them up by HUC12, assembles all the data, then puts them into the data structure that will move over to the server for them to. Can we run some of the ACPS with a coarser resolution elevation model? Yes, you could. In fact, some of our colleagues at the Rock Island Army Corps of Engineers have done so for the Cedar River Basin, a HUC8 watershed in Iowa and Illinois. They did nutrient marine wetlands, and I can't remember if they were doing anything else. And they were successful in doing so. Obviously, there's going to be some issues associated with that, and trying to extract, field level information from a 10-meter DEM is going to be challenging. The tools are stable enough so that if you wanted to do something like that, you could. I mean, you can assemble, and what the guys down at Rock Island did, they assembled all the data that are required for that particular tool. It ran for about a week on their computers, but it did finish. So, and they were pleased with the results we got. So, does the online database include the elevation data? No, it does not. We aren't in a position to do that. NRCS might be, but yeah. We don't have the capacity to do that. We are a research outfit, and so assembling these other data are not quite as time consuming and compute intensive kinds of processes. So no, we do not. Is there any opportunity to include the Gelder's hydro enforcement tool in the ACPF? Not at this time. We haven't really talked about that opportunity yet. I suspect that he might be amenable to something like that. We work with him every day, so I say. So Teresa Nelson from the Wisconsin DNR has shared with us that Gelder has shared with them the source code for the hydrologic enforcement process, and they're working on trying to get that to function fully.